In this video, we will be solving a problem from the application of helical springs, that is in railway buffers, that is in the buffer springs. So these are used for stopping the railway wagons or vehicles. So here in this picture you can see the part of a railway coach that is moving, and this can be stopped. This is known as buffer stops, and a buffer element which is provided with buffer springs will be attached to the part of this railway wagon, and that you can see here. So this is known as buffer, and within the buffer casing the helical springs will be provided. So we need to design this helical spring which is coming in this one, which is known as buffer spring. So here the railway wagon is moving with a velocity, so it is having some kinetic energy, and while stopping this energy will be absorbed by the spring. So based on that absorption, some force will be acting on the spring. Here that force is not directly given, but we need to find based on the conservation of energy. Then according to that we need to design. So here the railway wagon of mass 3 tons or 3000 kilograms. So this is the mass which is equal to 3000 kilogram. This is moving with a velocity of 3 meter per second in this direction. So this is having a kinetic energy you can find using half mv square, and this energy will be absorbed by these two springs. So these two springs, so I am taking a single spring. So in this one a force of F will be acting, and then this will be getting deflected by Y amount. Then the kinetic energy or the strain energy stored within the spring is equal to the work done, that is half average force, half into F into the Y. So this is the work done in a single spring. So here also another spring is here, where also the force is equally acting and deflection is acting. So the same amount of work will also be coming here. So the total work done can be found by multiplying it by 2. So I can equate this half mv square with respect to the work done in two springs, that is half into F into Y for a single spring, where F is the force acting on that spring, into 2. So now I can substitute the values, which is half into mass is 3 ton 3000 kilogram into velocity is 3 meter per second, it is 3 square, into half into F into, here it is given that Y, that means the spring is getting deflected by 160 mm. So I can substitute in meters, 0.16 meters into 2 for those two springs. So here only unknown is the force acting on the spring which is required for designing this one. If you are solving, you will be getting a force of 84,375 Newton. So this is the first step. Here the force was directly not given. It is given like based on the energy absorbed by the spring and the kinetic energy of this one. So now this can be used for the design of helical springs in a similar way that we have discussed in the previous video. So here we are having the spring like this. So this is our helical spring, and there will be some end condition. This end condition we need to assume, and here some force is being applied, and that force value we have evaluated, which is 84,375 Newton. So here we have explained already, shear stress will be produced, and we are having the expression for tau max, which is equal to 8ft divided by pi d cube into k. So this F now we are having, which is 8375, and D is the mean coil diameter. Here the mean coil diameter is given 200 mm. So the capital D value is also we are having, which is 200 mm, but the spring wire diameter we are not having. We need to find the value of this D. So here since D is unknown, the spring index is also unknown, so we cannot directly find the value of this, the Wahl's shear stress factor. So actually this K is a correction factor. In the previous question or in the previous video, we have taken the correction factor using the Wahl's shear stress correction expression, which is a function of spring index C, like 4C minus 1. So those equations you can see here. This is the expression for maximum shear, and in the previous case we have used this expression. But in this problem here we are not having any C value. Here we are having only the given with the value of capital D or this diameter. So we can use this correction factor or for the curvature effect, and including all the combined effect and curvature effect, we can use this correction factor, that is 2 into D by capital D the whole raised to 0.25. So I can take this K correction factor as 2 into d by capital D the whole raised to 0.25 I can take. So this tau max I can evaluate then this tau max will be equal to 8 into F we are having, which is 84375 into capital D 200 I am substituting in mm, divided by pi into D is the unknown, pi D cube, into K is equal to 2 into D by D the whole raised to 0.25, that is D raised to 0.25 divided by capital D, that is 200 raised to 0.25, and this will be equated to our limiting condition. This can be equated to the tau allowable in megapascal, and this value it is given in the question as 600 megapascal. So I will be substituting it as such, 600 megapascal or Newton per mm square. So we can solve this one. Here only unknown is the small d value. We can solve using the calculator, then we can find the value of this small d. So on solving, we will be getting the value of the spring wire diameter d as around 46.4 mm we will be getting. This is 46.4, that is the spring wire diameter. So this is we are getting at the end of the first step, the wire diameter 46.4 mm. Next step, we need to standardize this one. So if you are looking for the table for standardizing this one, that is the standard dimensions of the wire, here that range 46 is not available. So we can simply take the next higher even number as the standard diameter. So I can round or take the value of the spring wire diameter. Here it is 46.4, so we can take the next value as 48 mm, and we were given with the mean coil diameter which is 200 mm. So we are having the capital D. For the coil, I can take the inner diameter di for the coil, which is d minus d I can evaluate, and d outer I can evaluate, which is equal to d plus d. This is 248 and this will be equal to 152 mm. So this is the end of the second step. So in the third step, we will be finding the total number of coils. So total number of coils, the equation can be found here. That is, the deflection is given. So this equation can be used for finding the value of I, which is equal to y into g d raised to 4 divided by 8 into f into d cube. So this is equal to y into g d raised to 4 by 8 f d cube. This equation I can use. So here we are having all the values. The y, the deflection produced in the spring is equal to 160 mm. So the value I can substitute here. So this is 160 mm, and the rigidity modulus is also given, which is I think 84 GPa. So it is 84 GPa. In Newton per mm square I can substitute, which is 84 into 10 raised to 3. Diameter is also known, which is 48 mm. The force value we have evaluated, which is 84,375, and the capital D value is also known, which is 200 mm. So when you are solving this value, the number of active number of turns or coils, I will be becoming around 13.18. So this will be taking to the next full digit number, that is 14 turns or 14 coils. So this is the total number of active coil. In the next step, we will be assuming a suitable N connection. So from this table 11.4, we can take any one. So I will be taking this square and ground N, where the last column will be giving the values. If the active coil is I, then the total number of coils will be given by I plus 2. So I can write the total number of coils, which is equal to I plus 2, and that is equal to the 60 number of coils. And from the same thing, I can find the free length L0, which is equal to, the equation is given, I plus 2 D plus the deflection Y plus A. So here I is 14 plus 2 16 into diameter is 48, the axial deflection is 160, and this one axial gap I already explained the empirical relation, which is I minus 1 into 1 mm per coil. So I is equal to 14 minus 1, 13 into 1, 13. So if you are adding this one, then you will be getting the free length as 907 mm. So this is the free length of the buffer springs required. And next, from this same table, I can find the value of pitch, that is the distance between corresponding points for the helical spring, and that expression for finding the pitch is this one, L0 minus 2D divided by I. So L0 we are having 907 minus 2 times D, that is around 96 divided by I is 14. So if you are solving, you will be getting a value of around pitch is equal to 58 mm. So in the next last step is we need to find the stiffness of the spring. Stiffness or spring constant is given as simply the force acting divided by the deflection. So force is 84,375 Newton divided by deflection is 160 mm. So this value will be getting in units of Newton per mm, the spring constant or spring stiffness. Here the value will be around 527.3 Newton per mm. So this was in a way similar to the previous problem, but only the difference is here the force acting on the springs was not given, but instead it was given in the form of the energy of the railway wagon, and then we had to equate to the energy absorbed by the springs. So this is a typical problem for the helical springs, and hope you understood, and thanks for watching.